Hello, I'm Mr. McBrien. This is TEJ3E, a review of circuits. So, a quick note about circuits and electricity. We've talked about these things before, whether it be in science class or what have you. All circuits follow a few very simple rules. And this is true whether they involve a simple battery and an LED, or whether they involve millions of transistors contained in a CPU. So when it comes to computer engineering, there are at least two benefits to learning about these rules. The first is that we can get a better understanding of the computers that we're working on. And the second is that we can understand, conceive, and build interesting inventions that use these principles. Okay, so since we're just starting out, a quick overview of the unit. We're going to talk about the basic laws of electricity. We're going to talk about circuit theory. And we're going to spend a lot of time with schematics. And we're going to spend a lot of time building the circuits that schematics describe. So we'll do some soldering, we'll do some breadboarding. And then we're going to talk about more complicated circuits that don't typically get discussed in physics class. We'll talk about transistors and integrated circuits. And we'll do a bit of circuit analysis, really to get a better understanding for various devices, but to give us the tools we need to design our own devices as well. Okay. So what exactly is a circuit? A circuit at its most basic is a power source and a load connected in a complete closed loop. Okay, so that power source typically is a battery. And a load can be many different things. It can be a light bulb, it can be a motor, it can be a refrigerator, it can be many different things. Okay, we typically describe the components of our circuits with a few simple symbols. So we usually draw our circuits. Sometimes we'll describe them, but most of the time we will draw them, use pictures. And we'll represent the components in our circuits with these and a few other symbols. So a power cell, represented by a long and a short line. Multiple cells, represented by a series of these things, connecting wires, resistors or loads, open and closed switches. And certainly we'll distribute a few more symbols as well for our more complicated circuits later. Okay, sometimes we'll see drawings of circuits in cartoon form like this one. More commonly, we will see a schematic that uses the symbols we discussed in the previous slide. So in this case, these are representations of the same thing. 3 battery cells on the left-hand side, and 3 loads, whether drawn as resistors or drawn as light bulbs as shown on the left. Okay. We have a few tools that we can use to analyze the behavior of our circuits. So here's another circuit with representations of some of the qualities of a circuit. The current, represented by I. Again, we've got a cell that's providing the power for the current. We have a load, or a resistor. And in this case, we've taken an ammeter and placed it in series in the circuit, and we'll talk more about series and things later, but the ammeter is the device we use to measure the current in our circuit. Now, we can also measure the potential in our circuit using a voltmeter, and the only real difference here, the circuit's the same. The only real difference is that a voltmeter is measured what we call in parallel. So it works beside the circuit and measures the potential difference between 2 points. We'll certainly spend a lot of time with our multimeters, which have one of their functions is as a voltmeter. We'll spend some time on that over the coming days. Now, once we have a current in a circuit, we can then start to talk about the power that's consumed by our circuit. And we measure power in watts, and we can calculate it very simply. If we know the voltage and we know the current, then the power is the product of voltage times current. And so that's the energy consumed by a given device. So consumed by a motor, consumed by a bulb, consumed again by a refrigerator. And if we want to dig into the mathematics of it, we can say voltage is defined as energy per unit charge. We can say that current is defined as charge per unit time. And if we do the mathematics, we can cancel charge. And then we can say that power is energy divided by time. And here's an example of that simple calculation. If we have a 9-volt battery connected to a load that results in a 2 ampere current, what's the power consumed by the load? And the calculation is pretty straightforward. We're given our voltage and our current. We need to find out the power. P equals V times I, or 9 volts times 2 amps, 2 amperes. And 9 times 2 is 18. It's an 18-watt power consumption. Okay, and before you begin your calculations on your worksheet, one last thing to think about with regards to the circuits we're going to build over the coming time. You need to remember never to make a circuit connecting one terminal of a battery to another without something to consume the power in between the leads. This could be a light bulb, this could be a resistor. Without that load in between, you have a short circuit and you have the potential for a fire or an explosion. So there are, of course, some more safety concerns, and the safety handout is available to you in class, but this is the biggest one. Make sure that you don't short out your power supply. So go ahead and work through your worksheet, and we'll return to the question of circuits and deeper analysis tomorrow. Thank you, and have a great day.